You ever been faced with just a baffling list of database options? Feeling like, the wrong choice could maybe sink your whole project?
It's a common fear, definitely.
Or maybe you're just gearing up for a tech discussion, trying to get a handle on how our digital world actually stores all its data. Or maybe you're just plain curious.
Well, if any of that sounds familiar.
You've landed in the right place.
Today, we're doing a deep dive into a really foundational decision in building, well, pretty much any modern software.
Yeah, that choice between relational and non-relational databases.
Exactly. And our exploration today is based on a recent article that lays out the core characteristics of each pretty clearly.
Precisely. And look, our goal isn't to turn you into some kind of database guru overnight.
No, not in one go.
But we want to pull out the vital knowledge, the stuff that helps you understand when a relational approach is your friend, and when maybe a non-relational one might be the smarter. Okay, let's unpack this then, starting with the sort of the bedrock relational databases.
Right. So at their heart, relational databases structure data into organized tables.
Okay.
Tables,
Sure.
think of a really meticulously kept spreadsheet. Each row is a specific record, like one customer, and each column defines a particular attribute, like their name or address.
Gotcha. Rows and columns. Pretty standard.
But what's really significant here is the emphasis on the relationships between these different tables.
Okay, so the tables aren't isolated.
Not at all. They're interconnected. And this structure allows for really efficient data management and, importantly, powerful ways to query the data, pulling information from multiple tables at once.
Right, and the article we looked at really hammers home something called ACD properties, ACID.
Sounds technical, but it's fundamental.
Yeah, it might sound a bit intimidating, but it's basically a set of really strict guarantees. They ensure your data stays accurate and reliable no matter what.
Think of it like a contract.
Exactly. So atomicity, that means a transaction is all or nothing.
Like sending an email, it either sends completely or not at all. No half-send emails.
Perfect example. Then consistency, C.
That just ensures the database always follows its predefined rules. The data always makes sense according to the rules you've set.
Okay. I is for isolation.
Right. This prevents simultaneous actions, like two people trying to book the same seat at the exact same time, from messing each other up. Concurrency control.
Makes sense. And finally, D for durability.
This one's crucial. It guarantees that once your data is saved, it stays saved. Even if the system crashes or loses power, it'll survive failures.
Wow. Okay, so those ACID properties, they sound absolutely critical for certain applications.
Oh, totally non-negotiable in some areas. If you're dealing with financial systems, think banking apps.
Where every penny counts.
Exactly. Or managing inventory where accuracy directly impacts your business operations.
Knowing exactly what you have in stock.
Or even in those big, complex ERP systems, enterprise resource planning, that tie together all crucial business functions.
In all those cases.
Maintaining impeccable data integrity is paramount. That's where relational databases really, really shine.
That makes complete sense when you think about the stakes involved. Okay, so the article then points us to some well-known players in this relational space.
Yeah, the big names.
We've got MySQL. The source mentions it's the most widely adopted open source option.
Huge community, very popular.
Then there's PostgreSQL, described as sort of an advanced, highly extensible open source choice, maybe a bit more feature-rich.
Often seen that way, yes. Very powerful object relational system.
And for the bigger commercial needs.
There's Microsoft SQL Server, very robust, used a lot in large enterprises. And IBM DB2, another major player often found in big businesses.
Okay, and then there's one more, SQLite. Sounds smaller.
It is. It's lightweight, serverless, often used for embedded use cases. You might find it powering apps directly on your phone or computer, working behind the scenes.
Interesting. So even within the relational model, there's quite a diverse set of tools for different jobs.
Definitely. It's not one size fits all.
Okay, great. Now let's shift gears. Let's explore the other side, the world of non-relational databases.
Right. NoSQL, as it's often called. Non-relational databases offer a fundamentally different approach to handling data.
Different how?
Well, instead of sticking to those rigid tables we just talked about.
Rows and columns.
Yeah. They provide considerable flexibility in how data is actually stored. What's fascinating is the sheer variety of formats they can handle.
Like what kind of formats?
Things like JSON-like documents, which are very common on the web, simple key-value pairs, structures that model relationships as graphs, nodes, and edges, and even arrangements called column families.
Wow, okay, that sounds much less structured.
It is, and that adaptability is a key distinguishing factor. It's a major departure from the relational model.
Yeah, and the source material really highlights that this flexibility becomes a huge advantage when you're dealing with, well, vast quantities of data.
Massive amounts.
Yeah, data that's constantly changing or doesn't naturally fit into those neat, predefined tables.
Exactly. Think about things like user activity streams on a website, clicks, views, scrolls,
Constantly happening.
or the endless flow of posts and updates on social media platforms.
Right, or data pouring in from sensors, Internet of Things devices.
Or even multimedia content, images, videos.
In those kinds of areas, the traditional table format, it could become a bottleneck, right?
It absolutely can. It can be too rigid, too slow to adapt sometimes.
So the primary design focus for many of these NoSQL databases is different then.
It is. It's often about achieving high speed and, crucially, the ability to scale horizontally.
Horizontally, what does that mean exactly?
It means you can easily add more regular kind of off-the-shelf servers to distribute the workload as your data and user base grow.
So instead of buying one super expensive, powerful machine.
Right. Instead of scaling up, you scale out by adding more standard machines. It's often more cost-effective and flexible for really large scale.
Okay, that makes sense. And this ties into managing the sheer volume and speed of data today.
Precisely. But there's often a trade-off involved here.
Oh, what's the catch?
Well, it often involves strict consistency, which brings us to something called the CAP theorem.
CAP theorem. Okay, sounds important.
It is. We won't get into all the gory details today, but essentially, it describes the inherent challenges in distributed systems, which many NoSQL databases are.
Distributed meaning spread across multiple machines.
Exactly. And the theorem basically says it's really hard, maybe impossible, to simultaneously guarantee perfect consistency across all nodes, availability for reads and writes all the time, and partition tolerance, meaning the system keeps working even if parts of it can't communicate temporarily.
So we have to make choices, pick 2 out of 3 kind of thing.
That's the classic way to think about it, yes. Many NoSQL systems prioritize availability and partition tolerance, sometimes relaxing strong consistency compared to ACD-compliant relational databases.
Interesting trade-off. So,
Yeah.
okay, given these differences, how do you actually decide which path to take for your project?
Well, the article gives us some pretty clear indicators.
Lay them on us.
It suggests that a relational database is generally the way to go if your application needs complex transactions and joins.
Joins meaning pulling related data from different tables together.
Exactly. If you need to do intricate manipulations across different related pieces of data frequently.
Okay, what else?
Also, if your data has a very well-defined structure right from the start, and crucially, if those ACD properties we talked about are absolutely non-negotiable.
Like in those financial systems again?
Precisely. If you need those strict guarantees, relational is often the safer bet.
Okay. So when does NoSQL become the more compelling choice?
Conversely, NoSQL really shines when you're working with data that's rapidly changing, evolving, or doesn't fit neatly into a fixed structure.
Like that social media feed or sensor data.
And if your absolute top priority is the ability to massively scale out your system horizontally to handle enormous loads.
Scaling out, adding more machines.
Yes. Or if schema flexibility is paramount, meaning you want to avoid constantly redesigning your tables every time your data needs to change slightly.
So less rigid upfront design.
Right. If that flexibility is key, then NoSQL is definitely worth serious consideration.
The source material really emphasizes that the whole rise of non-relational databases is tied directly to this need to manage extremely large data sets efficiently.
It's a response to big data, essentially.
Yeah, and it points out they're particularly good for that unstructured data text, images, videos, and also for data that gets accessed really, really frequently.
Like those user activity logs or maybe session data for websites. Things you need to write and read very quickly.
So it's not surprising then, as the article notes, that companies dealing with just massive data volumes.
Social media giants, big online retailers.
They're often heavy users of these NoSQL technologies.
It makes perfect sense for their use cases.
Yep.
Examples mentioned include MongoDB, Cassandra, HBase, used by companies like Facebook, Twitter, LinkedIn, and others, dealing with huge scale.
Okay, but you mentioned earlier there's a lot of variety within NoSQL itself. It's not just one thing.
Oh, absolutely not. The NoSQL ecosystem is incredibly diverse. The article guides us through several distinct types, each with its own strengths.
All right, let's break those down.
Okay, first up, you have document databases. MongoDB is probably the most famous example here.
Document databases? What's the idea?
They store data in flexible, self-describing units called documents. Often these look like JSON. It's great when your data doesn't fit a rigid table structure or when the structure might vary from item to item.
Okay, flexible documents. Got it. What's next?
Then there are column store or wide column store databases. Cassandra is a well-known one.
Column store. How's that different?
Instead of storing data row by row, they organize data into column families. This can be really efficient for queries that only need a few columns from a very large number of rows. They're particularly well suited for things like time series data.
Ah, interesting. Like sensor readings over time.
Exactly. Or analytics data, things like that.
Okay. What other types?
We also have key value stores. Redis is a very popular example.
Key value. Sounds simple.
It is, conceptually. Data is stored as a collection of key value pairs. You have a unique key, and you store some value associated with it. They're all about achieving super high-speed storage and retrieval based on those keys. Great for caching, session management.
Fast lookups. Makes sense.
Then graph databases. Neo4j is a leading example here.
Graphs, like nodes and connections.
Precisely. They're specifically designed to model relationships between data points. Think of applications like social networks, who's friends with whom, or recommendation engines, people who bought this also bought that. They excel at traversing those connections.
Very cool. Seems specialized.
It is, but very powerful for the right problems. Then there are big table implementations. HBase is an example, based on Google's Big Table paper.
Big table. What's the focus there?
These are distributed storage systems designed for data that's way too large to fit in memory, needs random access, and often involves scanning large portions of tables. Think massive data sets needing flexible schemas.
Okay, so handling truly enormous scale again.
Yes, and the range keeps going. We also have spatial databases.
Spatial? Like geography.
Exactly. PostGIS is actually often an extension to PostgreSQL, but it adds capabilities optimized for storing and querying geographical data points, lines, polygons, essential for location-based services, mapping applications.
Right, finding things near you.
And finally, the article mentions multi-model databases. OrientDB is given as an example.
Multi-model, what does that mean?
It means they offer the versatility of integrating different data models, maybe key value, document, and graph capabilities, all within a single system.
So you get flexibility within the database itself.
Yeah, potentially the best of several worlds, though maybe with some compromises compared to specialized databases. The article makes a really crucial point here, though.
Which is?
The optimal choice among these NoSQL types, or even choosing NoSQL at all, really hinges on the specific nature of your data and how you intend to access and query it most often.
So as the article underscores in its design consideration section, it truly boils down to deeply understanding the specific needs of your application.
Absolutely. You have to ask, what kind of data are you really working with? How complex are the questions you need to ask of it, your queries?
What are your scalability demands now and in the future?
And how critical is absolute perfect data consistency versus, say, availability or speed?
Right. Understand the requirements first.
Always.
Okay, so summarizing the advantages of non-relational databases then, the article highlights
Their efficiency in handling really large-scale data.
their suitability for frequently accessed information like caching or logs.
The flexibility they provide for evolving data structures, less schema rigidity.
And their capacity to accommodate unstructured content like text, images, video.
Those are the big wins.
But it's not all sunshine and rainbows, right? The non-relational world isn't without its challenges.
No, definitely not. The article is balanced and points out certain drawbacks too.
Such as?
Well, querying can sometimes be more complex because there isn't one single standard query language like SQL across all NoSQL databases.
So each type might have its own way of asking questions.
Often, yes, that can add complexity. Also, setup and ongoing management can sometimes be intricate, especially for distributed systems.
Okay, what else?
They aren't always the best fit for data, requiring that strict transactional integrity we discussed.
Like the financial records.
Exactly. The lack of a standardized data storage model across all NoSQL types can also complicate things like migrating data from one system to another.
Right, less interoperability perhaps.
And as we touched on with the CIP theorem, They don't always guarantee full ACD compliance.
which can raise potential data consistency concerns in some situations.
It's that trade-off again. You might get amazing speed and scale, but potentially at the cost of immediate perfect consistency across the whole system.
And it's really important to reiterate, as the article does,
Yes.
that relational databases remain the superior choice for storing things like financial transaction data.
Absolutely. Precisely because of their predefined schemas and the absolute necessity of data integrity ensured by those ACD properties. You don't want eventual consistency with bank balances.
No, definitely not. So, okay, wrapping this up. The key takeaway seems to be that both relational and non-relational databases are incredibly valuable tools in today's tech landscape.
For sure. It's not a battle of one being inherently better overall.
It's about strategically selecting the right tool for the specific task you have at hand.
Exactly. You really need to analyze your application's data structure, think about the complexity of the queries you'll need to run,
Consider your scalability requirements, both now and down the road.
and be really clear about your consistency needs. How much consistency do you absolutely require?
Only then can you make a truly informed decision.
Right. And the article gives some helpful concrete examples just to drive this home.
Yeah, like if you're building a banking application or maybe an ERP system.
A relational database like PostgreSQL or Microsoft SQL Server is likely the most appropriate, sensible choice.
But well, if you're developing, say, a social media platform or a real-time analytics engine or maybe an IoT backend collecting sensor data,
Then a NoSQL database like MongoDB or Cassandra or Redis might be a far, far better fit for the scale, speed, and flexibility needed.
So ultimately, as the article concludes, the most effective decisions aren't about just jumping on the latest trend or buzzword.
No, definitely not. NoSQL is always better, or relational is dead. That's too simplistic.
It's grounded in a thorough analysis of the actual trade-offs involved for your specific situation.
That's the key. Understand the trade-offs.
Well, this deep dive has hopefully illuminated some of those key distinctions between relational and non-relational databases.
And maybe provided some clarity on when each type really proves most advantageous.
Yeah, hopefully demystified it a bit. Now, here's something for you, the listener, to consider. As we just continue to see this absolute explosion in the volume, but also the variety of data being generated,
It's not slowing down.
not at all. And the need for adaptable, scalable data storage solutions becomes more and more critical. What future innovations or maybe challenges do you foresee in this whole realm of databases? Are we going to see more hybrid, completely new paradigms? Something to mull over.
Good question to ponder.
Yeah,
The field is always evolving.
indeed. Well, thanks for taking this deep dive with us today.